Hello everyone, today I will start chapter 28. This chapter is about reflection of light and refraction of light. Reflection of light. Then we'll talk about the refraction of light also. So let us discuss the reflection of light. Okay, let me start from here. This is the very narrow path of light. We call this is a ray. Okay, very narrow path of light. That is what we call the ray. Very narrow path of light. This is the ray, and collection of rays like this. This is called as beam. This is ray. We can simply call single ray, but it is kind of impossible to get just the single ray. So simply we say very narrow path of light. That is what we call the ray, and this is collection of rays. So beam. This is collection of rays. That is what we call the beam. Okay, and you know that the light, when it strikes on the opaque surface, like this is opaque, okay, because light cannot pass through it, okay, and this is a plane mirror. This is also opaque object. This is also opaque. Light cannot pass through the object. If it is opaque, light cannot pass through the object. Okay, and there is another type of object like this. This is a glass slab. Light can pass through this, like your glass, eyeglass. Okay, so that is called as the transparent. Transparent. So transparent objects are like a glass, water, etc. Opaque like a wood, okay, paper, etc. And there is another type of object also, that is we call semi-transparent, or you can say translucent. Translucent, or this is semi-transparent. Semi-transparent. So the translucent or semi-transparent, only the partial amount of light pass through that object, like a wax paper. That is a semi-transparent object. All light, they cannot pass through that. Only the certain percentage of light can pass through that. That is called as the translucent. So simply you can say wax paper is the example. So we have three types of object: opaque, transparent, and translucent. Okay, this is really simple. Okay, when the ray of light coming from the the source, like a sun is the source of light, very big source of light. Okay, consider this is ray of light coming from the source. Here you have a source, light source. You have a light source coming from the light source, the ray of light, and this is your, let's say, plane mirror. This is the plane mirror like this. This is the plane mirror like this. This is a plane mirror. This mirror is same as the mirror you have in your bathroom, or simply we also call like you can say for your dressing you can use this. Okay, plane mirror. And what happens is when the ray of light is strike on the opaque object, it gets back to the same medium like this. So this phenomenon is called as the reflection of light. when the ray of light is striking on an opaque object, the light gets back to the same medium. That is called as the reflection. So this is, let me call, this is R, this is O, this is I. Okay, IO, this is incident ray. IO, this is the incident ray. Okay, OR, this is the reflected ray. Okay, IO, incident ray, OR, reflected ray, and this point right here we call the point of incidence. Point O, this is the point of incidence, and right here I would like to draw the normal. This is the normal. ON, this is the normal drawn at the point of incidence. Okay, so ON is the normal at the point of incidence. The ON, you draw the normal right here. Point O, this is point of incidence. So ON is the normal. Normal means it is perpendicular here on the horizontal surface. Okay. Now this angle ION, let me call this is theta I. Here angle ION, which is theta I, we call angle of incidence. Angle of incidence, theta I, this. And this angle RON, angle RON, let me call this is theta R, okay, theta R, and this is called as the angle of reflection. Angle of reflection. Okay, so I hope you get this. We have a plane mirror. Okay, you can consider like a M. Okay, let's call X, Y. XY is the plane mirror. IO is the incident ray. OR is the reflected ray, and ON is the normal drawn at this point. This point is called as point of incidence, and theta I, this is your angle of incidence, and theta R, this is the angle of reflection. And there is a law of reflection. Let me erase this first. Okay, so laws of reflection. This is also very simple. The first law is angle of incidence. Angle of incidence is equal to angle of reflection. That's it. The angle of incidence is equal to angle of reflection. So simply you can write down theta I equal to theta R. This is the first law of reflection. Angle of incidence is equal to angle of reflection. That is the first law of reflection. And the second law is this incident ray IO, reflected ray OR, and the normal at the point of incidence ON. All three lines here, three rays you can call, okay, they lie on the same plane. In this case, all these three IO, OR, and ON, they lie on this plane, plane of the board. This plane, okay, not like this plane. For example, if the light, coming this way, this is incident ray, and another ray it goes reflected ray this way, and you can draw the normal right here. So all three rays lie in this plane, okay. So the incident ray, the reflected ray, and the normal at the point of incidence, they lie on the same plane. The incident ray, reflected ray, and the normal at the point of incidence, lie on the same plane. Okay, so these are the two laws of reflection. Again, theta I equal to theta r, or simply you can say angle of incidence equal to angle of reflection, number one. And number two, the incident ray IO, reflected ray OR, and the normal at the point of incidence ON, all those three lines, they lie on the same plane. Okay, this is the second law. Okay. Now, let us suppose this is the plane mirror. This is the plane mirror, like this. This is the plane mirror. This is the plane mirror. Then, if I take this plane mirror and keep it like on the somewhere outside the room, if it is sunny, then you can see the very bright spot on the wall. Right? If you move it, then you can see the bright spot on the wall. But if you take this wood, and if you keep this, somewhere outside, when it is sunny, the sunlight is right here, but you don't see any bright spot, because the reflection from this object and reflection from this object, they are different. So this is a plane mirror. The surface is really smooth here. So what happens is, if the rays of light are coming like this, look, all rays, they are parallel. Then look at this, the pointer here, that this is the direction of the rays. Okay, so you always have to draw this pointer. So all these rays, they are parallel. So after reflection from plane mirror, what happens is, they go like this. The reflected rays, they are also parallel. The reflected rays, they are also parallel. In case of plane mirror, the incident rays, they are parallel. If they are parallel, the reflected rays, they are also parallel. And the image formed in this case is bright, shiny. That's why you see the bright spot on the wall. Okay, so this type of reflection we simply call regular reflection. Okay, another one, if you have like something like wood or paper like this, rough surface, and okay, let us suppose these are your incident rays and they are parallel like this. They are parallel. Incident rays, they are parallel. But what happens after reflection? One ray go like this, another one goes like this, another one this, and that, something like this. The reflected rays, they are not parallel. This is called as the irregular reflection, or simply you can call diffuse reflection. You can call diffuse reflection. So we see the object due to the diffuse reflection. If it is a regular reflection, then in that case it is really shiny, then it is very difficult for us. For example, if you drive on the road, like after 5 or 10 minutes after rain, the road has a layer of water there. Then if there is a layer of water, and if it is sunny, but there is a layer of water on the surface of the road, so the road is kind of very smooth, then in that case the regular reflection takes place. The day is sunny, consider that. After rain, it is sunny. Okay, so the rays strike on the layer of water, the road surface, which is very smooth due to the water there. And what happens? The regular reflection takes place. So the reflected rays strike on your eyes and it is shiny. You see the shiny road, and if the road is shiny, it is difficult to drive. Okay, so that is due to the regular reflection. So it is really simple things, regular reflection and irregular reflection. Okay, let us suppose this is the horizontal plane, and right here I want to keep the plane mirror. This is the plane mirror. Okay, and object is right here. This is the object. This is the object, And from here, from mirror to the object, this length, we simply call this of O, this is object distance. Object distance. Or people they use U also to indicate the object distance. Many people they use U, or you can use d sub O, whatever you want. Okay, d sub O, this is object distance. Object distance is the distance from the mirror to the object. Now, where is the image? Can you draw the ray diagram to show the image formed by this plane mirror? So where is the image? Okay, if you have to draw the ray diagram, you must need at least two rays coming from the object. Okay, so for example, let us suppose one ray is this, another ray is this. What is this? This is a plane mirror. So light reflects from this mirror. So draw the reflected rays then, like this. If you use the ruler, it is really good. And from here, it goes like this. Look, the reflected rays, these two reflected rays, they diverge like this. This and this, they diverge. They never meet them. To form the image, two or more than two rays, they must meet. Then those two rays, where they meet, at that point, the image formed there. So to form an image, two rays or more than two rays, they must meet at a certain point. So but look at this, the reflected rays, they do not meet because they diverge here in this case. But what we can do here is extend this reflected ray and this reflected ray. So let's see what happens. My diagram is not quite good. Okay guys, please use a ruler. Something like this. And this one, draw the dashed line, please do not draw the solid line. So look, these two extended rays, they meet here. This is the image then. Okay, this is the image. So the image formed behind the mirror. You keep the object in front of the mirror, but the image formed behind the mirror. You can observe this. Stand in front of the plane mirror, you can see the image behind the mirror, behind the reflecting surface of the mirror. Okay, so this is the image. And from here to there, this is your this of I, and this of I you can call image distance. Image distance. Okay. Now, if you measure this length, which is object distance, d sub O, and if you measure this distance, this length, which is image distance, and in plane mirror, object distance is equal to image distance. Okay. Number one, in plane mirror, okay, write down like this, in plane mirror, number one, object distance is equal to image distance. Okay, object distance is equal to image distance. That means you can write down d sub O equal to d sub I. Number two, the image formed by plane mirror is called as the virtual image. Okay, so the image formed by plane mirror is virtual image. There are two types of image. One is virtual image and another one is real image. The image formed by this mirror, this is a plane mirror. Look at this. This is a plane mirror. And the image formed by this plane mirror is virtual image. Why? Look at this. You can see I have a chalk, and you can see the image of the chalk. But How do you keep the film there? Look, it is behind the mirror. It is virtual. You can see that, but you cannot keep the right there behind the mirror. We cannot keep the film there. We cannot obtain that image on the screen. We cannot. So the image formed by this mirror, plane mirror, that is the virtual image. So image formed by the plane mirror, that is a virtual image. That is the image that cannot be obtained on the screen. That cannot be obtained on the screen. That is called as the virtual image. Okay, and there are other mirrors like we call the spherical mirror, like a convex mirror and concave mirror. I am not going to talk about the convex mirror and concave mirror today, but I can show you like this mirror. Look at this mirror. This is not plane mirror. Look, this is like a cave here. This is like a cave. So this mirror is concave mirror. We call spherical mirror. Look, this is like this thing. This is like a certain portion of the sphere. So we call the spherical mirror. But particularly this is the concave mirror. And the size of the mirror here. Look at this. The size of the object and size of the image, they are not equal. It depends where you keep the object. That makes a difference. Where you keep the object, that makes a difference. Okay, so this is a concave mirror. I cannot talk too much all about this mirror right now. First I have to finish the plane mirror. Okay, so and there is another type of the spherical mirror, and this mirror, look, this, the one I showed you before, that is concave mirror. Now this one, look, the reflecting surface is bulging out like this. Before it was like this, like a spoon. Okay, that was a concave. But this one, look here, this is your convex mirror. So we have basically two types of spherical mirror: concave mirror and convex mirror. This convex mirror we call the diverging mirror. Okay, convex mirror we call the diverging mirror, and the concave mirror we call the converging mirror. Okay, so if I get the time, I'll talk about this in future, but right now let us continue the plane mirror. So in plane mirror, object distance is equal to image distance, and the image formed by the plane mirror is virtual image. Okay, number 3, the size of the image and size of the object, they are equal. In plane mirror, the size of image, the size of an image is equal to size of an object. That is why the magnification is 1. In case of plane mirror, the magnification, you can write down magnification. It is simply denoted by M, magnification M. This is simply, you can write down. There are two ways. One is you can do this, like this of I, image distance divided by object distance. You can do this also. This is the formula to calculate the magnification. And this is equal to 1. You know that object distance and image distance, they are equal. Size of the object and size of the image, they are also equal. So the magnification, you can write down image distance divided by object distance, or you can also write down like this. You can also write down like I divided by O. I is the size of the image and O is the size of the object. Of course, this is also 1, because size of the object and size of the image, they are equal. Okay, so now I'm talking about the image formed by the plane mirror, and of course you are using the plane mirror. Everyone has a the plane mirror in your bathroom. Now if you want to see your full image, let us suppose you are 6 feet tall. What is the minimum height of the plane mirror, so that you can see your full height, full body? You can see your foot, you can see your head. So what is the size of the mirror? The minimum size. Okay, maximum is of course if you have like a 10 feet tall, of course you can see that. But I'm asking you, what is the minimum height of the mirror so that you can see your full image? For example, if you are 6 feet tall, so what is the minimum height? So please note down the minimum height to see your full image is half of your height. If you are 6 feet tall, the minimum size of the mirror, minimum height of the mirror is 3 feet. We can derive that formula also, but right now I am not going to do that. So the minimum height of the mirror to see your full image is half of your height. Okay, half of your height. So that gives you the full image. If you are 6 feet tall, you need 3 feet tall plane mirror. If you are 5 feet tall, then you need 2.5 feet tall plane mirror so that you can see the full image. Okay, I think this is all about the plane mirror and the reflection of light. And there is another one we call refraction of light. Refraction of light. For example, what happens is, if you take a stick, and if you dip the stick in the swimming pool or water, you can see that the stick is bent there. Like if you have, let us suppose this is water. Water is a transparent medium. This is water, okay? Then if you take a stick or a ruler or whatever, even if you keep your leg in water, half of your leg up to here in the water, then you see that your leg is bending there. So why? It is due to the refraction. So what is refraction? Let us suppose this is the ray of light, incident ray I, and this point is O, IO, incident ray. And right here you can draw the normal. This line, it is perpendicular. This is a normal. You can call N, O, N prime. This is a normal drawn at point of incidence. And what happens is, the light is supposed to propagate in a straight line like this. Like this. Like this. But what happened? This is air. This is water. So what happens is, at this point you have two different media. This is air, this is water, different media. Okay, so the speed of light change here. Then what happens is, light bent like this. It cannot go in a straight line. So this is your R. IO, incident ray. OR, that is your refracted ray. So light bent here. So this bending of light, when it travels from one medium to another medium, that is called as the refraction. The bending of light, when it travels from one medium, in this case from air to water, air to another medium, the bending of light when it travels from one medium, that is air, to another medium, in this case the second medium is water, is called refraction of light. Okay, again, the bending of light when it travels from one medium to another medium, that is called as the refraction of light. So now look at this. In this case, this is air, this is water. Here also you have air, consider. Okay, this is also air. So what happened? IO, incident ray. So the light bent here. OR is the, look, the dashed line is not the real ray. The solid line is the real ray. So this is the path of the light. So bend here. Now what happened here then? What happened here? Look, here. This is water, here you have air. So what happened in this, right here then, at this point? Here also this is water, this is air, two different media. So if you forget this portion, now consider this portion only. OR. And right here, this is another normal, you can draw another normal here. So what happened here then? water and air. So it is also the different media here. So what happens? Light also bend here like this. So look at this. Air and water. Think about the density of air and think density of water. Density of water is more than density of air. So we call this air. Air is optically thin medium. Optically thin medium. Or you can call rarer medium also. Rarer medium. Water. Water is optically thick medium. Optically thin medium and optically thick medium. Optically thick medium. Or you can call denser medium. Now look at this. In this case, first right here, light travels from optically thin medium to optically thick medium. In this case, the ray of light bends toward the normal. Look, this is the normal. This is the normal, and this ray, this one, it comes towards the normal. Now here, in the second case, consider this OR travel from optically thick medium, water to air, optically thick medium to optically thin medium. What happened? The rays of light, it move away from the normal. So if the ray of light is traveling from optically thin medium to thick medium, it bends towards the normal. Okay. If the ray travels from optically thick medium to optically thin medium, it moves away from the normal. That is the law of refraction also. Okay. So again, bending of light when it travels, from one medium to another medium, then that is what we call the refraction. And to go further, I have to define one new term here, that is we call index of refraction, and it is simply denoted by n. Index of refraction, people they use n, or you can also use mu. Index of refraction, n or mu, whatever you like. Okay, I simply use n. Okay, index of refraction. So what is index of refraction? N. It is simply speed of light. Speed of light in vacuum, which is simply c. We denoted by c. Speed of light in vacuum, c divided by speed of light in medium, v. Okay, speed of light in vacuum and speed of light in medium. Medium means like water or like a air. Air is we simply call like a vacuum, but still we can consider that. Okay, air, glass, any transparent material, okay, or whatever material we have, that is called as the medium. And vacuum, nothing, space, empty, that is a vacuum. So your index of refraction is speed of light in vacuum divided by speed of light in the medium. So you can write down index of refraction n, this is equal to c speed of light in a vacuum divided by speed of light in the medium, c divided by v. This is the formula to calculate the index of refraction. So what is this? Look, meter per second speed of light in the vacuum divided by again meter per second in the medium. Meter per second divided by meter per second, nothing, that's the one. No unit, okay? No unit. Index of refraction has no unit. And c, speed of light in a vacuum, it is a constant number. This number is 2.99 times 10 to the power 8 meter per second, or roughly you can write down 3 times 10 to the power 8 meter per second. This is the speed of light, 3 times 10 to the power 8 meter per second. This is the maximum speed of light, 3 times 10 to the power 8 meter per second, and nothing can move with this velocity. 3 times 10 to the power 8 meter per second. We cannot achieve that velocity. If I want to throw the object, we cannot get that speed so far. Okay, so far we cannot throw any object with that velocity. Speed of light 3 times 10 to the power 8 meter per second. It is better to memorize this. Okay, so index of refraction C divided by B. Now what happens is, if you take this like some kind of object, like a rod, if you take some kind of rod, I don't remember the name, but you take some kind of rod, and if you keep that rod in the, let's say, vegetable well, if you don't see that rod in the vegetable oil, that means the refractive index of vegetable oil and that rod is equal. If two transparent objects, if they have a same index of refraction, and if you put one object into another one, you don't see that object because their index of refraction is equal. It is good to know to answer the conceptual questions. Okay, now let us talk about the laws of refraction. Laws of refraction. Okay, this is a boundary line. Here you have water, optically thick medium. Okay, and this is water, optically thick medium, and this is air, optically thin medium. Let us suppose this is your incident ray, I, O. Here you have a normal. This is N, O, N prime. Okay, this is O here. Okay, and you know they are light bent here. Okay, so this is OR, refracted ray, and let us suppose N1 is the index of refraction of water in this case, this medium 1, okay, N1, and N2 index of refraction of water here. Okay, N1, this is index of refraction of medium 1, that is here. This is medium 1. Here is a medium 1. This is medium 1. Okay. Water, this is medium 2. So index of refraction of medium 1 here is N1, and N2, this is index of refraction of medium 2. This is water. Okay. And let us suppose this is theta 1, or you can say theta I also. Let me call theta I. And this angle here, this angle, look at this, this angle is theta R. Okay, theta I and theta R. So theta I is the angle of incidence. Angle of incidence. This angle ION. Okay, theta I is, this is angle ION, theta I, angle of incidence. Now NOR, angle N, let me call not N, let me call this is N, let me call this is N prime, okay. So make this ION prime, okay, because eigenvalue is the same name. This is N, this is my N prime, so angle ION prime, that is theta I, angle of incidence, and NOR, angle NOR, this is theta R, and this is angle of refraction. Okay, so please know this. And of course you have a two, this is a boundary line, we call the interface also. So two media, air and water. Air is optically thin medium and water is optically thick medium. Okay, so you define N1, N2, theta I, theta R. And there is a law of refraction, and the first law we simply call Snell's law. Snell's law, that is N1 sine theta I is equal to N2 sine theta I. This is the Snell's law. Or you can write down N1 sine theta 1 equal to N2 sine theta 2 also. It depends how you define the parameter. So N1 sine theta I is equal to N2 sine theta I. Sometimes using this formula you can calculate the index of refraction of the like a medium there, different media, using this formula. Okay, so this is the Snell's law, and the Snell's law is the first law of refraction, And the second law here is, look at this, the incident ray IO, the refracted ray OR, and the normal NO N prime, they lie on the same plane. It is kind of similar to the law of reflection. Okay. So the second law is the incident ray, the refracted ray, and the normal at the point of incidence lie on the same plane. Again, the incident ray, the refracted ray OR, the incident ray, the refracted ray, and the normal at the point of incidence, they lie on the same plane. Okay, this is the second law, and there is another one we can write down like this. If the ray of light is traveling from optically thin medium to optically thick medium, it bends toward the normal. What happened right here then? It bent away from the normal. If it travels from optically thin medium to optically thick medium, the refracted rays bend toward the normal. But if the light travels from optically thick medium to thin medium, the refracted ray moves away from the normal. You can make another law, okay? If the ray of light is traveling from optically thin medium to optically thick medium, the refracted ray bends, or you can say move toward the normal. And if the ray of light traveling from optically thick medium to optically thin medium, the refracted ray bends, or you can say move away from the normal. Okay, so if the ray of light is traveling from optically thin medium to optically thick medium, the refracted ray bends towards the normal like this. Here, optically thin medium. What are optically thin medium? Look, IO, incident ray. Now OR here, this refracted ray. Now look, this refracted ray come closer to the normal. Here is the normal. But if the ray of light is traveling from optically thick medium to optically thin medium, look at this. OR, look, this is water. OR is in water, optically thin medium. Now, let me call this is R prime. Here you have here. So, OR to R prime. Look at this is optically thick medium, and this is optically thin medium. So, R prime, refracted ray, it moves away from the normal. This ray R prime, this is a refracted ray. People they also call emergent ray also. Emergent ray is also the refracted ray. Okay. So ray of light traveling from optically thin medium, that is also called as the rarer medium, to optically thick medium. The refracted ray bend towards the normal, And if the ray of light is traveling from optically thick medium like water to optically thin medium like air, it bends away from the normal. You can make, this is the third law of refraction. Okay, so this is about the laws of refraction. Now look at this. This is water. Okay, water, and this is air, and let us suppose this is incident ray, and here you have a normal n prime, this is O, this is I. In this case, ray of light is traveling from water to air, that means optically thick medium to optically thin medium. So what happened in this case then? What happened? What do you think? In this case, I told you that the ray bent away from the normal, like this. This let me call like this, I1 OR1. Okay, so in this case, look at this. If this is your theta I, this angle is your theta r. If the ray of light is traveling from optically thick medium to optically thin medium, the angle of incidence is less than angle of refraction. If the ray of light is traveling from optically thick medium to optically thin medium, the angle of incidence is less than angle of refraction. Now take another line, another ray like this. Let me call this is I2. Again the I2O, this is incident ray inside the water. Now we know that if the light travels from water to air, the refracted ray bends away from the normal. Now let us suppose this is your R2. This OR2, this is your refracted ray. Now in this case, if you measure this angle, look at this. NOR2, this is your 90 degree, this angle here is 90 degree. If the ray of light is traveling from water to air or optically thick medium to optically thin medium, it bends away from the normal. But if the angle of refraction in optically thin medium is 90 degree, angle NON is 90 degree, then the corresponding angle in optically thick medium is called as critical angle. So this angle here, everyone, this angle, this one, this angle is called as the critical angle, and it is simply theta C. Okay, this is theta C. So again, what is critical angle? Critical angle, it is theta C. What is this? When the ray of light is traveling from water to air or optically thick medium to optically thin medium, the ray of light, the refracted ray, move away from the normal, bends away from the normal. Okay, if the angle of refraction in optically thin medium is 90 degree, light, please, you have a condition here, light travels from optically thick medium to optically thin medium, and if the angle of refraction in optically thin medium is 90 degree, then the corresponding angle in optically thick medium is called critical angle. If the angle of incidence in optically thin medium is 90 degree, then the corresponding angle in optically thick medium, corresponding angle of, let me write down incidence, okay. Again, if the angle of refraction in optically thin medium is 90 degree, then the corresponding angle of incidence in optically thick medium, that is called as the critical angle, and it is denoted by theta c. Now let us consider N1 in this case, because light travels from water to air, so I call N1 is the index of refraction of water, and N2 here it is index of refraction of air. Now use the Snell's law. What is Snell's law? N1 sine theta I equal to N2 sine theta r. This is the Snell's law. Now N1 in this case, N1 is index of refraction of water, so write down N1. Now what is theta I? Theta I is critical angle here. I am talking about the critical angle, so the angle of refraction is 90 degree. So sine theta c, then theta I, angle of incidence here we call the critical angle because the angle of refraction is 90 degree. N1 sine theta c, this is equal to N2, everyone, N2, the index of refraction of here we can simply take 1, okay. So let me write down 1 sine theta r. What is sine theta r? Sine theta, look, theta r is 90 degree in the optically thin medium, so you can write down sine 90 degree, okay. So what is sine 90 degree then? You know that sine 90 degree is equal to 1. If you use your calculator, you can get this. Sine 90 degree is equal to 1. So you can write down N1 sine theta c, this is equal to just simply 1. 1 times sine 90 degree is 1. So N1, index of refraction of optically thick medium here is 1 over sine theta c. Or you can write down sine theta c, this is equal to 1 over N1. Okay, so using this formula you can calculate the index of refraction if the critical angle is known, or you can also calculate the critical angle if the index of refraction is known. And different transparent medium, they have a different index of refraction. Different index of refraction of course, and different critical angle too. Different transparent medium, glass has one, water has another one. For example, glass, the index of refraction of glass is roughly 1.5. Roughly, different types of glass, they do have a different index of reflection, but roughly it is 1.5. The index of refraction of water is, I think it is 1.33. Please check this, okay, in a textbook, or you can do the Google search. Okay. Similarly, the critical angle is also different for the different transparent medium. I think for water it is 48.8 degree for water. For water, the critical angle theta c for water is, I think, 48.8 degree. Roughly 49 degree for water, okay. So different transparent medium, they have a different critical angle, they have a different index of refraction. So this is about the critical angle. So please keep in mind, to define the critical angle, light travels from the optically thick medium to optically thin medium, number one, and the angle of refraction must be 90 degree. In the optically thin medium, your angle of refraction must be 90 degree. Okay, now I1, I2, R1, R2, incident ray, different incident ray. Now what happens if you take another ray, incident, let us suppose this is I3. Now look, I3ON is angle of incidence in optically thick medium is greater than critical angle. What happens in this case? Think about it. If the angle of incidence, if the angle of incidence in optically thick medium is greater than critical angle. What happened in this case? In this case, simply light get back to the same medium. Now this is your R3. If angle of incidence in optically thick medium is greater than critical angle, then ray of light get back to the same medium, or simply you can say reflect, or simply like reflect. Reflection takes place. This is called as total internal reflection. This is called as total internal reflection. Okay. So if the angle of incidence is greater than critical angle, then in that case ray of light get back to the same medium, or simply ray of light reflect. This is called as the total internal reflection. Total internal reflection. Okay, you need to know this. You need to know this total internal reflection. So the condition is light must travel from optically thick medium to optically thin medium, number one. Number two, the angle of incidence must be greater than critical angle. So for water, let us suppose there is a fish. Right here, there is a fish. For example, this is a fish. And the fish look at this direction, in this direction. This is a fish. Okay, this is the fish, and if the fish look in this direction, what does this fish see? The fish is looking from here, making an angle greater than critical angle. What happened in that case? Do you think the fish can see the atmosphere here? No, because the light reflects. And if this fish is looking from here, making an angle greater than critical angle, in that case the fish cannot see the environment outside the water. The fish can see the bottom of the pond. Fish can see the water, because look, this ray go here and reflect back. This is what we call the total internal reflection. Okay, so this is about the total internal reflection. Please look at your textbook also, because my video is long. I cannot make more than an hour. I already spent 58 minutes, so I have to stop right here. Okay, I'll bring another video, different chapter. Okay, thank you.